To this OCR A-level chemistry video on enthalpy changes. The first thing that we need to know is that some chemical reactions have enthalpy changes, so energy changes, that are either exothermic or endothermic. An exothermic reaction releases energy, or an endothermic reaction absorbs energy from surroundings. Therefore, the exothermic reaction is going to have a net increase in the temperature of surroundings, whereas endothermic reaction, temperature of surroundings decreases. Okay, so this arises because of certain energy changes caused by breaking and forming bonds in a reaction. So breaking bonds is endothermic. It absorbs energy, whereas forming bonds is exothermic. So it releases energy to the surroundings. Therefore, in an endothermic reaction, energy absorbed by breaking the reactant bonds is greater than the energy released to form product bonds. So exothermic is just the exact opposite. Energy absorbed to break reactant bonds is less than energy released when forming product bonds. So this explains why in an endothermic reaction, there's a net increase in energy in the system that is taken in from the surroundings, while in an exothermic reaction, there's a net decrease. Energy is released to surroundings, temperature surroundings increases, but the energy within the actual chemical system decreases. We can show this in enthalpy profile diagrams. So you have your diagrams like this. It's energy and progress of reaction. So if we start reactants here, we have our activation energy. We'll get to that in a second. So this is the energy needed for a reaction to take place. As our products. So this is an exothermic reaction shown by negative delta H, as the net energy decreases as the reactants have more energy than the products. Whereas in an endothermic reaction, you have the reactants here, high activation energy, and the products have more energy than the reactants. Here the spec tells us what we've just discussed, activation energy. So this is the minimum energy. So the amount of energy that is absolutely required for a reaction to take place. When discussing enthalpy changes, there are a few key words that we need to look at. The first thing that we need to understand is the idea of standard conditions and standard states. With standard conditions is just a general term for general conditions that you could have in industry to facilitate a reaction. There's generally 100 kilopascals. You might know it as 101 kilopascals could also work, to be more exact. 100 kilopascals works as well. And 298 degrees Kelvin. So this is approximately 25 degrees Celsius. As we all know, converting from Celsius to Kelvin is at 273. So, in the enthalpy change of reaction is just what it says on the tin. It's the energy change associated with the stated equation. Just any reaction. So if you had O2 plus H2 plus 2H2O, the So 2H2O, so it's all balanced. The energy change of this exact reaction, these exact proportions, would be the enthalpy change of reaction. It's the enthalpy change of formation. It's formation of one mole compound from its elements. So this would be carbon in solid state plus hydrogen gas produces methane, CH4 gas. And this works because we only have one mole of product. If it was something different, if we had 2 moles, that wouldn't give us the enthalpy of formation. We'd have to divide all the coefficients by 2. That's like in the earlier example. This delta H wouldn't give us the enthalpy change form or formation for water. We would have to have half O2 gas. State symbols are important here because you want these in standard states. We can't have oxygen as a liquid because that's not usually how we find oxygen. Plus H2, which is H2O, so only 1 mole of water is formed. The enthalpy change of combustion is similar. It's a complete combustion of 1 mole of a substance. So if we had CH4 plus O2, CO2 plus H2O, let's just balance that. 2, 4, 2O2, yeah. 1 mole of methane. So this would give us a delta H of combustion. Finally, the enthalpy change of neutralization is the formation of 1 mole of water from a neutralization reaction. So that's acid and a base. So if we add HCl plus NaOH produces NaCl plus H2O, the energy change from this reaction would give us a delta, the energy of neutralization. Something that I should have mentioned earlier is that for all of these definitions, you have to mention the standard condition and standard states. All of these enthalpy changes don't work unless they're in standard conditions and standard states. Okay. Finally, for this part, we can find the actual energy released from a reaction through this formula, Q equals mc delta T. So Q is the energy in joules, m is mass, typically this is in grams for our case, C is the specific heat capacity, specific heat capacity. So this is the amount of energy needed to increase the temperature of 1 gram of a substance by 1 Kelvin. So our temperature, we know that's going to be Kelvin. So our units for specific heat capacity is going to be joules per gram per Kelvin. So we're going to use this in our practicals in our PAG 3. Okay, so here I've got the method for PAG 3.2 where you have to find the energy change of a reaction. So one of the tips that we need to use is that we need to assume that the volume of this, to assume that the density of the solution, the aqueous solution, is the same as the density of water. Therefore, the specific heat capacity is going to be the same. Water equals C of solution. And that makes calculations a lot easier. As we know, the known value for specific heat capacity of water as 4.18 joules gram Kelvin. Since we also assumed that the density of the solution equals the density of water, we can also say that the mass is going to be 30 grams, because 1 centimeter cubed equals 1 gram. Okay, there are also a few control measures here. The polystyrene cup is used to insulate, so that reduces the energy that's lost to surroundings. So the temperature change is more valid and accurate. So closer to the true value. Accurately weighs sample water contain between 2.5 grams and 3 grams. So this would be with the electronic mass balance to reduce percentage uncertainty, since the resolution is very high. Continually stirring, that ensures even distribution. So the reaction can occur not, the reaction can occur more smoothly. So instead of the carbonate just sinking to the bottom. Mm, Okay. So heat absorbed would be measured by Q equals mc delta T. So mass would be 30 grams times 4.18 specific heat capacity of water times delta T measured by the thermometer to find the temperature change. Okay, for plug 3.3, this is slightly different because you're trying to find the enthalpy change of combustion of ethanol, or rather different alcohols. So you'll have at least 5 different alcohols. Okay, so for this one, you'd have to measure a known mass or a known volume of water. So you could have fill a beaker with 250 centimeters cubed water. And for this one, this would have to be a copper beaker because you'd be heating this one directly with the spirit burn as it's conducted. Overall, finding the energy change is similar. It's exactly the same. Q equals mc delta T. Since it's the water that's being heated, we'll use the mass of water. So in this case, it will be 250 grams. Specific heat capacity of water is 4.18, and we can find our temperature change. But the key difference is we want to find the energy of combustion, enthalpy change of combustion. So we'll have our energy change divided by total moles of ethanol now. Moles of ethanol. So we can find the energy released per mole of ethanol. Okay, we've discussed before about how the energy related to bond making and breaking. So the average bond enthalpy is energy absorbed to break 1 mole of gaseous bonds. It's an average because actual bond enthalpies might be different to each other. There are obviously different scenarios that can cause different bond enthalpies. So what we have as our bond enthalpy is just an average of a lot of bonds being broken. And this part right here, the exothermic and endothermic reactions in terms of enthalpy changes with breaking and making of chemical bonds, that's what we discussed right here at the start. So in endothermic, the energy absorbed by breaking reactant bonds is greater than energy released to form product bonds. At exothermic is absolutely the opposite. The energy absorbed to break reactant bonds is less than energy released when forming product bonds. So there's a net release of energy to the surroundings. It's more energies being released to surroundings, so there's a delta H is negative. It's negative, and for endothermic, delta H is positive. Finally, we've got a concept in enthalpy change called Hess's law. So, despite the fact that we don't need the actual definition, it's worth understanding where it comes from. So, if we've got A, B, so the energy change from A to B will be the same no matter which route you take. So, this means if we have an intermediate here, let's call it C. So, energy change from A to C, then C to B. So, this energy change is absolutely equal. It's exactly equal. That's H1 equals H2. And these can help us find enthalpy changes, a lot of unfamiliar scenarios, like find the enthalpy chain reaction from combustion, chain reaction from formation, and get from unfamiliar enthalpy cycles. Finally, just a little bit of techniques and procedures for enthalpy changes. So this is more practical aspect. So something that we could have mentioned in our practicals is limitations. Why isn't our result exactly the same as what we get from a textbook? So some limitations are energy is lost surroundings to the surroundings. You could also say the reaction was incomplete, such as incomplete combustion. It's always worth it to be more specific, as often reaction is incomplete. This is a bit vague. It's not likely to be credited with marks in the mark scheme. If you want to improve it, we could say instead of using a polystyrene cup, we could use a copper calorimeter. These are what's used in industry, and these are a lot better as it means that there's minimal energy lost to surroundings. Finally, we'll go through some exam questions. Start with this. Why do all average bond enthalpies have a positive value? And we'll say this because energy needs to be absorbed to break reactant bonds. Or not reactant, they need to be absorbed to break any bonds. Since they're absorbed, it's going to be positive because there's a net increase of energy in the system. Part B says, part 2, telling us CH bond enthalpy, kilojoules per mole. Okay, that's fine. So you want CH4. CH4. So in methane, you just know that there's 4 CH bonds. That's what we want, so we'll call that 4x. H2O, that's 2 OH bonds. 2 times 4 is 64. Then, for the product, we're going to minus everything. So minus 3 times 4, 36. Plus the CO carbon monoxide, that's going to be 1077. And that all equals 195, positive 195. That's the enthalpy change. So we can calculate this as being 4x plus 2 times 4, 464 is 928, equals plus 2580. So 4x equal, bring 928 to the other side, so that was 652. So x is 413 kilojoules per mole. So our bond enthalpy is positive 413 kilojoules per mole. Okay. Part 3. Hydrogen gas household fuel. Enthalpy formation of water is this. So the energy released 260 meters cubed of hydrogen to household fuel. Okay, give it to 3 significant figures in standard form. Okay, so the equation that we have here is H2 plus O2 produces H2O, the half. So, like we said before, only 1 mole of water is being produced so that we can use our enthalpy change of formation. So, 1 mole of hydrogen, therefore, releases 285.8 kilojoules per mole, and we have 60 meters cubed. So we know that 1 mole equals 24 decimeters cubed in standard conditions, standard temperature and pressure, and 60 meters cubed is 60,000 decimeters cubed. Well, that's 24 to get 2,500 moles of hydrogen. So 2,500 times 285.8 equals 715. So this energy in kilojoules, sorry, that is released because 285.8 is a kilojoules per mole. So you've got 714,500 to standard form, that's 7.145 times 10 to the power 5. And we want 3 significant figures, so our final answer is 7.15 times 10 to the power 5 kilojoules. Okay, finally, this is a Hess cycle question because we know we've got enthalpy changes formation. So part 1, easy 1 marker, conditions of temperature and pressure, use standard enthalpy measurements. So this is 298 Kelvin. Pressure is going to be 100 kilopascals. Okay. For understanding enthalpy change of formation of nitrogen oxide, we'll first write the equation. So we have 4NH3 plus 5O2, 4NO, 6H2O. Okay, so the energy change of this reaction, so it is minus 908 kilojoules per mole. To make this easier, I'll have a new intermediate. Since we've got change formation, that gives us a clue that we need the original elements in their standard states. So that's going to be nitrogen gas, oxygen gas, plus hydrogen gas. So enthalpy change of formation of ammonia is minus 46. So we'll go up from the elements to ammonia. 4 times minus 46. Oxygen is an element in itself, so it doesn't have enthalpy of formation, so we can just leave that as is. Nitrogen oxide, that's what we want. So up from the elements to nitrogen, so it goes 4x. And from this to water, 6 times minus 242. So we can follow our route, go down here. So we'll flip the sign. So 4 times 46, positive, plus 4x, plus 6 times minus 242 equals minus 908. So that gives us 184 plus 4x minus 1452 equals minus 908. So rearranging all that, we have 4x equals 360, x equals 90 kilojoules plus. So an enthalpy change formation of nitrogen oxide is 90 kilojoules per mole. Thank you for joining me. Hopefully that would make sense.